In this video, we're going to learn about acid-base equilibria. So you'll recall that strong acids ionize 100%, or so we assume. So for example, if you put HCl in water, you don't have equilibrium arrows, you just have a straightforward rightward arrow producing H3O plus and Cl minus. If you wanted to, you could write an equilibrium expression, and for any K that involves an acid, you can write it as Ka. That is equal to the concentration of H3O plus times the concentration of Cl minus, both of which are aqueous, divided by the aqueous concentration of HCl, omitting, of course, the liquid water. For this reaction, the Ka is 1.3 times 10 to the 6th power, meaning that we have a whole lot of the H3O plus and Cl minus and almost no HCl. And that's why we can make this approximation that there's 100% ionization. And this is the case for all the strong acids. Perchloric acid, the Ka is so large, it's over 10 to the 9th. And nitric acid, even though it's only on the order of 10 to the 1st power, we still have so much more product than reactant that we can assume about 100% ionization. But with weak acids, they only partially ionize. And so they're going to have very low Ks. They're going to be much less than 1. So for example, for vinegar, or acetic acid, the Ka is 1.8 times 10 to the negative 5th. And if you look at this table here, we've got a whole bunch of Ks. Note that these are all weak acids and their Kas are all 10 to the negative 2nd or less. So let's say that we had to determine the pH of acetic acid and it were 2.00 molar. If it were a strong acid, you just take the negative log of the 2.00 and you'd have your answer, because the strong acid's concentration of H3O plus would be the same as the concentration of the strong acid. But here, we don't know the percent ionization, but we definitely know that it's not 100%. So what we can do is write out our equation and create an ice table. So our initial concentration of CH3COOH is 2.00 molar. And we're going to say that, all right, we're dropping some of this acetic acid into water and seeing what happens. Initially, there really isn't any H3O plus. There definitely isn't any CH3COO minus. But the change, well, for every one acetic acid that breaks apart, we get one acetate ion and one hydronium ion. We don't know how much, so we just say X is the change in each. So our equilibrium concentration of CH3COOH is going to be 2.00 minus X, and for our H3O plus and CH3COO minus, it's going to be X. We can now substitute into our K, knowing that K is equal to 1.8 times 10 to the negative 5th. This is something that you have to look up on a table, but we were just talking about it a few slides ago. Substituting in the concentration of H3O plus as X and the CH3CO minus also as X, and the concentration of CH3COOH as 2.00 minus X, we have this equation that we can solve for X. Except that's complicated, and you normally would have to use a quadratic here, but we can actually approximate the denominator to be 2.00 because X is going to be so small. This is a weak acid. It really doesn't ionize very much at all, so we know that X is going to be very small. And since X is very small relative to that 2.00, it's like stepping on a scale. You weigh however many pounds, and then you take off your sock. Yes, you are lowering your weight, but you are lowering it by such a small amount that it doesn't even register. So we can actually make this approximation, and it really shouldn't do for a weak acid. It really shouldn't do very much at all, unless you had an extremely dilute concentration of the weak acid, like 0.00001 molar. It's really not going to make much of a difference. So let's make this approximation, which makes solving for X much easier. So if our X is 0.0060 molar, we can say that X is the concentration of H3O plus, and the pH is the negative log of that X. And so simplifying from here, the negative log of 0.0060 is 2.22. So note that for our 2.00 molar solution of acetic acid, the pH is only going to be 2.22. It would be less than that if it were a strong acid. Now, weak bases, of course, they partially ionize as well, and this is the other side of the coin. So if we have NH3, it will react with H2O to form NH4 plus and OH minus. We can say for this, there's a Kb, just an equilibrium constant, the B designating that we're talking about it behaving as a base. And as it happens, the Kb for NH3 is actually the same as the Ka for CH3COOH. It's a complete coincidence. But we don't have to do a calculation here because, frankly, it's exactly the same way that you would problem solve with Kb as you would with Ka. It's important to note that for any conjugate acid-base pair, the Ka times the Kb will be equal to the water constant of 1.00 times 10 to the negative 14th. So take, for example, phosphoric acid. Its Ka is going to be 7.5 times 10 to the negative third. And its conjugate base, if you remove an H plus from it, you get the dihydrogen phosphate ion, and its Kb will be 1.3 times 10 to the negative 12th. And if you multiply this, Ka times the Kb of the conjugate base, you will get approximately 1.0 times 10 to the negative 14th. Any variation is really a rounding error. And you can really see that perhaps in, for example, where is it? Well, the hydrogen sulfate ion, 1.2 times 10 to the negative second, and the sulfate ion of 8.3 times 10 to the negative 13th. This is important because this goes back to our principle of the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. As we get up here towards high Kas, note that the Kb's are going down as we have Kas getting smaller to 10 to the negative 13th or so. The Kb is going to increase. A very strong base means you have a weak conjugate acid. A weak conjugate acid to the point that it's essentially not acidic. And of course, a weak conjugate base, the weaker the conjugate base, the stronger the acid. So let's talk about some salts. So for example, NaF being a salt, it's the salt of a strong base, NaOH, and a weak acid, which is HF. If you were to react NaOH and HF together, you would get NaF. And previously, you may have learned to look at it like my hydroxide, this is a strong base, my HF is a weak acid, so the basicity kind of overpowers the acidity, and we end up with a pH that's north of 7. If we had, for example, NH4Cl, and that would be the salt formed from a strong acid, HCl, and a weak base, NH3. In this case, the pH would be less than 7. But let's talk about why and how we get to these pH values that are not equal to 7. We can say that the Cl minus, if we break this apart into ions, the Cl minus really can't behave as a base because it's the conjugate base of a strong acid. The whole point of strong acids is that they're strong because they form their conjugate base, and then their conjugate base is stable. It's not going to go back and pick up an H+. On the other hand, the NH4 plus can behave as an acid because it's the conjugate acid of a weak base. It has an H that it can give, and it's pretty decent at giving up that H. So what we can do is say that once you dissolve the NH4 plus or NH4Cl in water, the NH4 plus will react with water. The Cl minus, right, I could write Cl minus plus H2O, that really is not going to form HCl, HCl plus OH minus. And that's why I have the left arrow there. It's just not going to happen because the Cl minus is too weak of a base. But again, that NH4 plus is acidic enough to make this reaction go forward at least to some extent. So let's say that we have a 0.10 molar solution of NH4Cl at 25 degrees Celsius, and the Ka for NH4, actually it's really NH4 plus, at 25 degrees Celsius is 5.6 times 10 to the negative 10th. What we can do is set up our equation. NH4 plus H2O goes to NH3 plus H3O positive, and we can make an ice table. So initially we have a 0.10 molar solution of NH4 plus with absolutely no NH3 and H3O plus. We can say that some amount of the NH4 plus does break apart. How much? We don't know. Let's say it's X. And for every X NH4 plus that is lost, we gain an NH3 and an H3O plus, and we get to these equilibrium concentrations. From here, we need to write our Ka, which is equal to the concentration of the product side over the reactants. And with substitution, we can say that our K of 5.6 times 10 to the negative 10th is equal to our equilibrium concentration of NH3 times that of H3O plus, both of which are X, over our equilibrium concentration of NH4 positive, which is 0.10 minus X. Even in this case, because the K is so small, it's 10 to the negative 10th, we know that this reaction really is not going to go very far forward. X is going to be very, very small, and relative to even 0.10 molar, it's going to be almost nothing. So 0.10 molar minus a very small number is still very close to 0.10 molar. So with that approximation, we can have a much simpler problem to solve, and we can get to X being equal to 7.5 times 10 to the negative 6th, which is a molarity. So from here, we know the pH is the negative log of the concentration of H3O plus, which, as we know, is equal to, 7.5 times 10 to the negative 6 molar. And from here, we can get that our pH is 5.12. So for our solution of the salt of a weak base and a strong acid, we do get a somewhat acidic solution with a pH of, in this case, 5.12. So I hope this video has been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.